So, Mark, you're the CEO of this company called Pattern Computer. Why don't we start by you explaining what those two words mean when you put them together?
Sure. If you think of the entire history of what computers have done for human beings till now, it's really simple. We ask a computer to do something, it does it. Payroll, whatever. It does it better, faster, bigger, but it's always something we ask for. It's limited by our knowledge. It's limited by our request. It's limited by our hypothesis. So we took the crazy idea of, what if the world were more complicated than we thought, than we could conceive? What if we don't use a hypothesis at all? Could we build a computer system which wouldn't rely on us to make the ask, but would just give us all the patterns in that information? That's what Pattern Computer does.
Kind of out-of-the-box concept there, Mark.
It's brand new.
So could you give us the significance of such capabilities and in layman's terms?
Sure.
And then why should we care about this?
You bet. So imagine that you have a big problem. Cancer, big problem. People have been working on cancer for how long? Forever. There are a lot of smart people out there, a lot of money being spent. They're all great people. It's a good thing to do, solve that problem. But it represents a typical problem. So until now, that would mean that you'd go to school, go to grad school, go to med school, become a researcher, get an idea. You think, Paul, that this gene X, may be the new answer to why women get breast cancer. And you're going to test that with an experiment. And you spend the next 10 years working on that. You might be wrong. Or you might be half right. Or there might be more to the story. And the compute systems that you'd be using, including supercomputers, would be unable to go past a fairly low number of parameters in terms of the two areas here. One is how complex is the question compared to what you're asking. And cancer is complicated. And how high is the dimensionality of that problem? So as one example, we're looking at a data set right now that's about 125,000 people around the world who have a certain type of cancer. And there are 39 million parameters per person.
Wow. Wow.
High dimensions.
Yes.
And as I can tell you appreciate, there are either few or no tools that can do that. So what you end up doing is having a tool that'll do a one or a pair, twosies, onesies, but not able to look and come back with a sophisticated, complete answer about the patterns that were in that data at higher levels. Mm-hmm. So in one example that we explained at Splash, we had a situation where we were looking with Larry Smarr at the human microbiome. Mm-hmm. So you take all the tens of thousands of species of that and then ask how many proteins they make. And you're at a crazy number, which is something like 10 to the 40th, which I'm told is more sand grains than there are in the world or in the universe. It's a big number. It's a bigger number than a supercomputer could attack. And so, oops, that's going to be hard. And we were able to take that potential number of permutations and reduce that to 39 proteins and then to 9.
Wow.
Yeah.
Wow.
So the ability to take these very high dimensional problems and not lose the information that's in the data set and bring it down to a lower dimensionality where you can do intense mathematical work is part of what the system does.
Wow. Thanks for doing that in layman's terms, too.
Did that work?
That worked.
All right.
When we talked last year, as we were sitting here, but in another venue, about the book you just published, The Pattern Future, it seems like there's a link here from your book and this company. So can you help us understand that linkage?
You bet. So as everyone who's been here before knows, I've spent my whole career just about working on pattern recognition. Mm-hmm. And one of the things I learned pretty early in that project was you could come up with predictions about things that you had no right to be able to get right. And by no right, I mean you had no training, you didn't belong to that company, you didn't study that subject. How could you possibly know more than the CEO of Microsoft or the researcher who's working on that thing? And it wasn't because you were smarter, it was because you were doing something different. And this is what leads to the difference in our semantics between what we call pattern recognition and pattern discovery. So if you looked at multiple databases, if you had the time in your life, right? If you literally had the time to spend reading a lot, seeing a lot of things, which may not be related in other people's minds, but actually have a relationship of some kind, you start to see meta patterns, higher patterns, that others haven't taken the time to find. And those things teach you amazing predictive things that you wouldn't ever have stumbled upon by accident. So whether it's illegally smoothing earnings by a corporate chief, which I found one time, whether it's China firing missiles on Taiwan, which I predicted pretty accurately when the oil price collapsed, I don't know anything about any of those things. But by watching across a broad range of metrics, you can come up with these understandings, which generally are true. So that question turned into, it's in the book, right? But that question turned into, is it possible that we could build a computer system that would do the same kind of work?
So your writings led to a company.
I think that the study led to the company.
Okay.
Yeah.
All right.
Yeah. 20 years of increasingly becoming amazed at the power of this higher level pattern recognition led to the idea that you could actually build a compute system that could do that kind of work.
Okay.
And that there were something to find. There were actually pattern discoveries out there to find.
Well, maybe to help further clarify and break this down a little bit, can you help us understand the difference between this pattern computing and supercomputing and quantum computing?
So I mentioned a minute ago, we worked with Larry Smarr, who's got his own personal supercomputer. He's one of the main supercomputer experts in the world. So at his beck and call down in San Diego at UCSD, and he had worked for a number of years, I won't say how long, but a long time on this microbiome project that I mentioned.
Right.
He also was able to use the most advanced tools around. He had some stuff out of Stanford, I won't mention what it's called, but he had access to whatever he wanted to have access to. And within about 2 weeks of doing runs, we had found things that he'd never found before. And he literally said, how did you do that? So it isn't just a brute force problem. You can't just brute force your way into getting to a higher level of understanding. It just doesn't work. What you're doing with a supercomputer is basically building thousands and thousands more every generation of chips and tying them all together as best you can and then running the same algos. That last bit doesn't work. So you really have to have new mathematics and a new systems architecture, which is less about size and more about elegance, I guess, or focus. And if the focus is simply find all the patterns that are there, that's your job. That's what we built you for. Both in terms of hardware, in terms of software, mostly software, that's what we've done. So it's very different from a supercomputer.
Okay.
Quantum computing is pretty well understood, I think, by the folks who care about it now, been around for a while. We're still probably years away from a general quantum computer working well. But the idea there is much more about what is a bit. Is there 2 bits per byte, or are there more? What is a qubit? How many qubits do you have? When we finally build a really good general quantum computer, one of the beautiful things about the systems architecture of Pattern is that we look forward to new chips. And we see clouds and we see things like a quantum computer as a coprocessor in that design. So every time there's a new discovery of hardware, of chips, that feeds what we're trying to do. And it's an important part of the idea of pattern computing that you allocate the tasks to the best chip. So the heterogeneous chip architecture is inherent to what we're trying to achieve there.
Okay. Thank you.
Yeah.
Again, in the spirit of clarification, trying to break this down, because pretty heady stuff here, Mark. What's the difference between pattern recognition and pattern discovery?
So everyone does pattern recognition, right? Every brain does it. Today, AI is in everything that you buy. It's everywhere. It's a commodity, I think. All of that is based on pattern recognition. And God bless it. It's great stuff. I'm a big believer. Here is one difference. And it's probably the key difference. To get at these bigger discoveries, unknown, which we call pattern discoveries, instead of telling the system what we want, we let the system tell us what is there. And that is a night and day, black and white difference from yesterday to tomorrow. So when you do that, you open your mind and your understanding to anything that comes. And what an exciting idea. So instead of assuming something about cancer or about asteroids, whatever it's going to be, dark energy, you don't have to do that. The system will come back and give you everything, and then your problem is that's a lot of stuff.
Right.
You may have thousands of patterns there. And so it turns out that once you've got that done, you're just started, because the bigger problem is how do you rank them? So we had to build engines that are ranking engines as well as the discovery engines.
Right.
But that is the difference. And what you find are things that are unexpected. So you find things that are expected, which is good. That proves the case, right? You actually are getting it done. So if you find breast cancer causes that were already well described, perfect.
Mm-hmm.
Thank you, Lord. That means we're on track.
Right.
But if you find 90% more things which you've never seen before, nobody else has ever seen before, that gets exciting. And somewhere in there, many of them are trivial. They might even be, I don't think they'd be wrong in that sense, but they're not very important. But there are going to be some things in there that are just mind-blowing. Mm-hmm. Particularly what we've experienced is, as an example with cancer, with breast cancer and lung cancer, is people will have found this one gene, that's important. This one gene, that's important. You look at all the literature, well, these 9 genes, they're important. But the most complex answer generally is these 2 work together. Well, life is more complex than that. So,
Right.
so is cancer.
Yeah.
So it turns out, well, maybe there are 6 things. Maybe there are 10. And they're all working together. And maybe there are 50 of these families. So which ones are the most important? So we did a study that we were starting to show around on lung cancer, where you can actually see all the genes that have been described so far that have any connection whatsoever to lung cancer, picture 1, and then the refinement of that after you run it through the pattern system, all of the families of related, all the structures, right, all the actual families of genes, and how tight are they, which relationships between every,
Mm-hmm.
and then which ones already have drugs that are known for lung cancer, color those some color, and then, by the way, which ones are druggable by existing FDA-approved drugs which no one knows apply to this cancer instead of some other. So no big, long clinical run to get to
Right.
success there.
Right.
And there are a pretty large number of those.
Oh.
So that kind of thing, where you can shorten the runway to success
Yep.
for treating cancer, find things which people hadn't found before, see the complexity of it, and hopefully treat people and solve their problem.
Right. I
That's
like the
good.
acceleration to market of repurposing
Yes,
drugs.
yes.
That's super. So we have some angel investors out there. I don't know if we have any VCs out there. So I'll ask the question on your behalf. So Mark,
So Paul.
so who else has a pattern discovery computer either on the drawing boards or commercially available?
Well, you never can answer the drawing board question. I don't know. But in terms of commercially available, I don't think anybody does. So this really was a fairly original thing. This is something which wasn't part of the normal university course. You wouldn't run into this working at Google or somewhere else. You really had to start from scratch and go at this thing, and for different reasons than usual. We're not trying to sell advertisement. We are not trying to sell ads. So it's a whole different motivation, and a more basic one, I guess.
Mm-hmm.
But as far as I know, I'm sure others will follow, but we haven't seen anybody yet.
Okay. Kind of a piggyback question, again, for people that might be thinking of investing. And by the way, this is not an investment forum. I didn't want to go there. Does it actually work? So you're in a frontier, and how do you know whether what you're doing is working or not? How do you get at that?
Right. So I mentioned when we did our first run on breast cancer, we found, these things are already known. It was a wonderful day because you want to find things that are already known.
Mm-hmm.
That's one way that you know that your system is working.
Right.
A better way, in some sense, is you go to other people who are outside experts. So at our Splash event, we had 3 people who were world famous who had used the system in their own work and benefited in their own research by using it, and got on stage and were willing to talk about it publicly. Mm. So you kind of get, you get outside testimonials from people who are well respected, who say, this is something new, this works well for my own work.
Mm-hmm. Wow, good.
I'll mention a little tease, which we haven't announced yet.
Okay.
And that is, pretty soon we'll be able to make an announcement, I hope within a week or 2. We've just done a 10-year master partnership agreement with a very well-known cancer research center that everybody here will know the name of when they hear it, for covering genetics and cancer to work together. So it's a big deal for us.
Good. So Mark, back in 1970, I started with the Burroughs Corporation selling mainframes, and what we sold was a big chunk of iron, an operating system, and the customers left to either develop their own software or maybe find some snippets of software. So I'm intrigued about your pattern computer and how is that architected, and when it's available, what does that mean to how the users will take advantage of it?
Mm-hmm. So in terms of the structure of it, the system's architecture of it, it literally was a blank piece of paper. So it wasn't like you had any rules. You know, the teams that started this had no rules about it, except what it had to be able to do. And there was actually a eureka moment during this, which actually happened in a bathtub. And that's all I'm going to say about that.
Okay.
But our committee's like, right, and everyone, wow, that's it. And people are very, very, so Ty Carlson is our CTO. He ran the Alexa team. He ran Office 360. These are very sophisticated veterans. And they saw this, and they said, wow, that would do it. Mm-hmm. And part of that would do it meant that would scale. Because scaling is the hardest part of the problem if you can solve the first part first. So would it work, and then would it scale? And it felt to these guys like, wow, that's going to work. Mm-hmm. So if you looked at it now, of course, we don't show designs and blueprints to everybody, but you would see an ingestion engine. And so a lot of work went into very large databases with lots of problems, noisy, dirty. How do you ingest them quickly? Mm-hmm. And we were able to get a system so that, I'll give you an example. The first time it took like 2 or 3 weeks manually to mess with all the stuff. Next time we got it done, we could run it as 2 seconds on the front end of a real run. So that meant that we could ingest every iteration, mm-hmm. which made the ingestion part of the iteration, which made it much more advantageous in terms of exploring things. Mm-hmm. And then there's the engine itself, so very complicated. And this is new mathematics. So in almost every case, there's an existing chip or existing math, but literally new mathematics where people are telling us, this has never been done before. You should publish this. You should write a paper. You should write a book about this. We're going, not today. No. We're going to make money first and we'll do it later. So, but it's an indication of the level of fascinating excellence that you have to bring to a problem of this caliber, right? Sure. It's like respect the problem. Mm-hmm. This is a big darn problem to solve. Mm-hmm. It's pretty gutsy to say that somebody could do this, whether you're saying, could you find a system that will find major discoveries in your data that you can't find? All your guys that you've been paying for 15 years? Mm-hmm. That's gutsy. Right? Yes. And also just in the compute environment where we've both grown up, it's like, you're going to come up with a system which is so systemically different that it does something qualitatively better than Michael Dell's doing or somebody else. That's pretty gutsy. So the backside of it is have respect for the problem. Right. And these people are working literally at the level of pure mathematics in the beginning, turning that into code, turning the code into better code, and then running that in new ways on chips. Mm-hmm.
You said there was a third part?
The third part is what you see. What you see is what you get. Right. So imagine that the greatest challenge in a way is after you're all done, you may have thousands of things, or hundreds of thousands, and then you need to show their aspects. How do you do this with a customer who may be a CEO and doesn't mm-hmm. care much about tech, And so it's very important to have good visualization techniques. Okay. So we're working with the top visualization institute in the world to help us. And we've got guys internally who are in the core team who've come from lifetimes at the national labs working on visualization. And we're not done yet. I think we have another year to go before we get that where I want it. But we are already at a place where, I'll give you an example, 2 examples. One is at the May event, we showed that we could portray the genetic expression contribution to breast cancer for a given patient A and B in such a way that compared to today's oncologists, you would have a much better chance of what we call walking a patient into safety. Because you could literally manage risk for that patient in a new way that hadn't been done before. And it would show you differences between patient A and patient B, which had been masked before because there were too few dimensions being discussed. But if you knew that there were 6 genes instead of 1 or 2, you go, oh, let's look at it in multi-dimensions, visualize that, give it to an oncologist, color code it, and then it'll become obvious that this person is in tough straits, and this person just needs a little bit of a push on that one gene and maybe survive.
Mm-hmm. Wow.
Yeah.
Wow. All right. Okay, so this will conclude the interview. Mark, thanks for taking us a little bit deeper into this subject.
Thank you, Paul.